So welcome to today's class. Today we'll be talking about a number of topics, but the first one is GLM models for risk ratios. This is where we stopped last week. Last week we went through GLM in general, and we went to logistic regression. So as a reminder, I'm going to do a quick review of last week's class. And if you remember, I said that GLMs are generalized linear models. And the key thing about GLMs is that they're structured in such a way that there are two parts of them that you have to change, and then you have a number of different kinds of models. Okay, so GLM, the general structure of the GLM model is, let me write that separately, GLM outcomes, and tilde, and exposure. This is the general structure of all models. You've probably seen that in linear regression. But for GLM models, usually you would have the data, and then for GLM models, you have to specify the family. I'll call that parameter 1. And then you have to specify the link, and I'll call that parameter 2. Okay, this is the general structure. And we can change parameter 1 and parameter 2. So in linear regression, which is where we started from, parameter 1 is Gaussian. Okay. Parameter 2 is identity. And this is identity because basically what it means is that we're asking R to not make any change to the form of the outcome. Okay, let me take that again. Parameter 1 is Gaussian. Essentially, we're saying that this is a continuous variable we expect to be normally distributed. Remember that those density curves that we have seen are called Gaussian curves. Okay, those density curves, ones that we use to illustrate skewing, and we used to understand histograms, normal distribution. They're called Gaussian curves. So when we say that parameter 1 is Gaussian, we're basically saying to R that we expect that this model will be normally distributed and the outcome is continuous. When we say the parameter 2 is identity, we're saying we preserve the identity of the outcome, make no changes to it. Okay, and that's why we can easily interpret linear regression using the same units as the outcome. Okay, you remember all of this from our discussion of linear regression. And then last week, we saw logistic regression. For logistic regression, parameter 1 is binomial. And it's binomial because the outcome is a 0 or 1 outcome, right? That's why I said you must always code the outcome as 0 or 1. Okay, so parameter 1 is binomial. It's saying to R that you expect an outcome that is 0 or 1. Okay. Parameter 2 in logistic regression is logit. And logit here, remember I said that logit refers to probability, the logarithm of the odds. Okay, which is also the logarithm. I remember that odds is probability divided by 1 minus the probability. Okay, This is the odds. So that's the logistic regression. Basically, you're saying to R that when you obtain the relationship between the exposure and the outcome, I want you to express this in form of the logarithm of the odds. Okay, so that's really what we're asking R to do in logistic regression. But today we're going to see a number of two other models, and these two other models, the reason why they're not as popular is because 30 years ago, when computers were not as advanced as they are today, these models will break down often. They will still break down today, right? But because they broke down often, people, and because they're kind of complicated to calculate by hand, people will generally prefer to use logistic regression. But today, in many cases, you're able to implement these models in R and in software. So people are beginning to talk about them more often. So today we'll talk about log binomial. Okay, the log binomial. And the log binomial is actually a model where instead of the logarithm of the odds, we're taking the logarithm of the outcome itself. Okay, so we're taking the logarithm of the outcome itself. So the parameter in this case, parameter 1 is also binomial, but parameter 2 is the log. Okay, parameter 1 is binomial, parameter 2 is the log. Now, in logistic regression, the outcome that you get when you exponentiate, you obtain odds ratio, right? We all know this by now. But in log binomial, when you exponentiate, you obtain the risk ratio. So let's take an example. What kind of data would you use for log binomial? Essentially the same kind of data as for logistic regression. The key difference is that you want to obtain the odds ratio in logistic regression. Here you want to obtain the risk ratio. And why would we want to use the risk ratio? Because the risk ratio is typically easier to interpret. Okay? The risk ratio is typically easier to interpret. So this is an example, R is greater than 80, which is a 0-1 variable. We've seen that before. And the exposure of interest is female. Now, we could present this as, we could use this in logistic regression, but we can also do log binomial regression. And so this is the code that we would use for that. And so if you run this code, and like I said, the family is binomial, the link is log. And when you run this code, you will get, oh, because I have not run all of this from before, sorry. So the data set is not loaded, the variables are not created. So I just asked it to run everything from above, so we can just carry on from where we are. So now we have RDS. And so now when we run this model, this is the model output. Okay, so it's very similar to the logistic regression, but because we know that the link here is a log and not the logit, right? We will interpret this beta estimate differently. Okay, we will exponentiate like we do for logistic regression, but when we exponentiate, we'll interpret this as a risk ratio, not as the logistic regression, which gives us odds. Everything else is the same. You interpret the significance the same, the p-value is the same, but this is not the logarithm of the odds. Okay. So if we exponentiate, the risk ratio that we get is 0.74, and this is the confidence interval. Any question? Any question on this point? Or is this completely clear? We understand it. Do I need to go over this again? It's a very quiet class today. Okay, so I'm going to keep going. Seems fairly simple enough. There's another type of model that gives us risk ratios, and that's the log Poisson. And that is the log Poisson. And here, I want you to pay extra attention because we will talk about the log Poisson, but I would also extend these GLM models further and talk about Poisson models in general. And that's not in the code, but we will develop it as we go. I'll talk about Poisson models in general. And the reason why I want to do that is so that you can see the contrasts. Okay? Log Poisson model is basically flipping, or let me say, changing the outcome from the binomial structure to Poisson. Can somebody remind us what a count variable is? Anyone wants to remind us?
It's a variable that is not continuous in that we're using just integers, whole number integers. For example, number of children or so.
Okay, so we'll go from like 0, 1, 2,
1, 2, 3.
5.
Exactly.
Okay, don't go yet. If we have a 0 or 1 variable, do you think that we could think about it as a count?
If the outcome is either 0 or 1?
Yes.
I think we could.
Yes, we could. Because if in a Poisson we're going 0, 1, 2, 3, 4, 5, 6, but it doesn't mean that we absolutely have to go the whole length. We could literally stop at 0 or 1. And so when we stop at 0 or 1, we could therefore use the Poisson family of models in the context of 0 or 1 or binary variables where we would have used logistic regression. Let me take that again. Count variables, like Debbie had reminded us, are variables that are integers, 0, 1, 2, 3, 4, 5, and the like. They cannot be broken apart. You can't have decimals. Now, when we have a count variable that is 0, we can have a count variable that is 0 or 1. It doesn't have to go further than 1. And because we can think about a count variable as having 0 or 1, it means that we can really apply the models that depend on count variables. We can apply them to binary variables where we only have 0 or 1. And that's really what we're doing here. And the reason why we do that here is that there's 2 reasons. One, when we have a count variable that is 0 or 1 and we take the logarithm, so when we have a count variable that is 0 or 1 and we can use the Poisson model, when we take the logarithm, we will obtain the risk ratio. So if you have interest in a risk ratio, then we can use this model. That's one. You might ask, why don't you just use the log binomial that I just showed you? And the reason is because the variance of the log binomial tends to be wide, and sometimes it just breaks down. And so a lot of times, and I don't have an example for you, but this happens so often. And the first time it happens to you, you might think that you're doing something wrong, but it happens so often that when you run the log binomial model, it will break down. You will not get an output, you will come up with an error. So in those situations, when you have the log binomial breaking down, but you're still interested in the risk ratio, you can use something called the log Poisson. Okay, the log Poisson, and it's called the log Poisson to make it easy for you to realize that this isn't the log in the Poisson family of models, but we're taking the log. Okay, so the log Poisson. So everything else is the same as the model that we just saw, except that the family is Poisson. Here as well, the link is the log. And if you go back to the logistic regression that we saw, the family is binomial, the link is a logit. So it's different from the logistic regression in two ways, but it's different from the log binomial in only one way, which is the family. Okay? So everything else the same. We can use this output 0 or 1, and the right side of the model can be the same as we know. We talked about this before. The right side of the model can be the same. So when we run this model, we will get a beta estimate that, as you can see, looks very similar to what we obtained with the log binomial. The variance is also the same. The p-values are very similar. So the beta estimate is the same. The p-values are very similar. The standard error is similar, but not the same. The standard error is more akin to what the p-value looks like. So you can see. But one thing that you will note is that the standard error for the log Poisson tends to be larger, and the p-value tends to be further away from 0.05. So if the p-value for log binomial was 0.1, then this is more likely to be like 0.2 or something like that. So that means that for log Poisson, you're less likely to find statistical significance. So these are all, things that you will understand in the back of your mind as you make the choices for which models you want to use. And the reason why you might want to use the risk ratio instead of the odds ratio is because of interpretability, right? When we're thinking about the occurrence of disease, we're very often thinking about it in the context of the probability or the prevalence. And this, remember that the prevalence and the risk are the same. Now, the risk ratio compares the occurrence or the probability in those who are exposed to those who are not exposed. It's a simple structure to understand. It goes from probability, which is where most of us are thinking about things, to the risk ratio, where we're just comparing the exposed to the unexposed. And that's different from the odds ratio, which complicates it a little bit, because the odds and the probability are different in that the probability is just simple, the p, while the odds is the p divided by 1 minus p. Remember that we've talked about this. And because of that structure of the odds, it's a bit challenging to wrap your head around if you're not someone who is comfortable with gambling or who is comfortable with the games of chance. So a lot of clinicians actually prefer the risk ratio to the odds ratio. Okay, and this is why we continue to show these variables, these models, so that there are options for people who want the risk ratio. Another way that we could have done this is to calculate the odds ratio and then convert it to the risk ratio, but that's sort of roundabout. Okay, so I've shown you today the general structure of the GLM models. Okay, as a reminder, I talked about the fact that there are two things that change, parameter 1 and parameter 2, and I've just called them parameters for convenience. And so linear regression, there's two, it's Gaussian and identity, and it's identity because I said we're basically saying nothing is changing, don't make any changes, don't do any transformations to the outcome. Don't make any transformations to the outcome. In logistic regression, the parameter 1 is binomial. We're basically saying that's the family is binomial. We're basically saying to R that the variable is a 0 or 1 variable, and we're asking to provide us the logit, which is the logarithm of the odds. And when you exponentiate, we'll obtain the odds ratio. For log binomial, parameter 1 is binomial, parameter 2 is a log. And for log Poisson, like we just saw, Poisson is someone's name, so you write that in caps. Parameter 1 is Poisson. Parameter 2 is log. And when you exponentiate, same thing, we get the risk ratio. And I said that I would introduce the Poisson family of models. And so I'm going to scroll all the way to the end. I'm going to scroll all the way to the end. And talk about the Poisson family of models very quickly. The Poisson family, these are for count variables. And we have seen the first one, which is the log Poisson. Essentially where we want to obtain the risk ratio. Okay. Here again, for the Poisson family, so remember that the family is always Poisson. The link is where there are changes. And for log Poisson, the link is a log. Okay. So basically, we're only going to make changes here. Okay. Now, the question is, why would we want to make changes? We make changes because of the outcome, the nature of the outcome. We haven't talked extensively about Poisson models in this course. And so I expect that what I'm going to be showing you might be very introductory. But many standard courses don't really talk about Poisson either. So this might be your only exposure to this in the course of this course. Now, when we talk about count variables, an example is the number of children. Okay, number of children. And if in this resident doctor's data set, you were interested not in the mental health score, job satisfaction, workload as the outcome, but you're interested in the number of children as the outcome. As you can see, is 0, 2, 1, 3, 4, right? And you're interested to know whether female resident doctors are more likely to have more children than male resident doctors. Okay? So let's look at the analysis and then we'll go back to explaining. So let's call that fish, because Poisson means fish. So GLM, so we're basically going to label the model fish. So GLM, and the outcome that we're interested in is children. So we have tilde, and then the exposure we're interested in is gender. Our data is RDS, and the family is Poisson. Okay, and the link could be log. Okay, basically this is the log Poisson, and we're basically saying, maybe I could put this here. What we're basically saying in this case is that the outcome that we obtain will be expressed in risk ratio. Okay, and written that up there, but that's very important. So we can run this model and ask it to present the, so if, this is what the beta estimate looks like, 0.199, and the p-value is 0.23, which tells us that this is not significant. But if we wanted to obtain the risk ratio, if we wanted to obtain the risk ratio, we would see by exponential. Let me do it one by one so you can see. Exponentiate, and we'll use the coefficient function, exponentiate. We'll use the coefficient function and ask R to provide for us the coefficient of the model that we call fish. So the relative risk in that model is 1.22. This is the intercept. So we can ignore that. Relative risk in that model is 1.22. If we wanted the confidence interval, we use the confounders function, and it will provide for us the confidence intervals for the intercept as well as for the variable that we're interested in, 0.88 to 1.68. So this is log Poisson. We've seen this. But I'm going through this again to show you that changing certain things will change how we interpret. But you're the one who has to be careful of when to use what. Okay? Now, this is log Poisson, but do you think that we should have exponentiated to obtain the risk ratio? Do you think that what we're obtaining here is actually a risk ratio? What do we think? Remember that I said that for us to obtain a risk ratio, this has to be a 0 or 1 variable. Okay? This has to be a 0 or 1 variable. And because this is not a 0 or 1 variable, it's a count. And we have children, we have people who have children that are 3, 4, 5. So that means that even if you add the log here, what you're getting is not a 0 or 1. It's not a risk ratio, it's something else. Okay? Now, in the basic Poisson model, the correct thing to have done here would have been, so I'll just call this Poisson. In the basic Poisson model, the correct thing to have done here would have been to leave this as identity. Now, if we leave this as identity, can someone tell us what this means? Anyone wants to guess?
Well, you told us earlier that it preserves the identity of the outcome.
Yes. And so, because this is the number of children, what will this mean?
I am not sure how to interpret that, quite frankly.
It's challenging, yes. Yeah,
Yes.
you're absolutely right. So it's challenging because now we're breaking, essentially, what this is the main difference. Okay? So when you ask it to preserve the identity, what you're asking it to do is to obtain the mean of the number of children in men and the mean of the number of children in women, or in the male resident doctors and the female resident doctors, and to compare that. So this is essentially telling us that on average, resident doctors who are male, who are female, because yeah, have a 0.2 have 0.2. It's weird because 0.2 is what's it called? Is now a fraction. So we will interpret that as a percentage. 20.2% more likely to have children. Okay. Another way to have interpreted this would have been to say that they will have 0.2 children more than male resident doctors, but that would sound weird because you can't have children who are half. Okay. If this were a number of days, it would have been easy to interpret that as, so let's say this was days on the ward, we would have found it easy to interpret that as on average 0.2 days more. But the key takeaway here is that Poisson is for count, and identity preserves the structure of the outcome. And so what we're really dealing with is the mean. So this will be 0.2 more children than male counterparts. So let's interpret that way and keep it that way, even though it's not very meaningful. Okay. Now, if we take the log, however, okay, resident doctors who are female have 0.2 more children on average than male counterparts. So this is kind of weird. It's not a way that we would usually interpret this. If we take the log, however, which is what we had seen before, okay, now it will convert this to a percentage. Okay, so if this were log, this will become 20% more. Female resident doctors have 20% more children on average. And if this were minus 0.199, it would be 20% fewer children on average. I don't know if this is clear. Let me take that again. For Poisson, if the outcome is 0 or 1, we obtain the risk ratio. If the outcome is a count, as in here, we don't obtain the risk ratio. We cannot obtain the risk ratio for a count variable. Okay. So when we use identity, it preserves the structure of the model, of the outcome variable. But because in this case, it is rendering this as 0.2, and we cannot have a 0.2 child, the disciplined way to have done this would have still presented this as resident doctors who are female have 0.2 more children on average. But an option would have been to have taken the log instead, which would have presented us with the option of using percentages. So this is the Poisson family of models, and you can go into different examples. So if you use identity, you preserve the structure, and the question that you will then have is it reasonable to interpret it that way? Should I take the log so that I can present it as percentage more or percentage fewer? Okay. Any questions? So the key takeaway, therefore, is for Poisson models, the only time you are exponentiating is if you want the risk ratio and if it is reasonable to obtain the risk ratio, which is in the context of 0 or 1 variables. Any questions? Or this is perfectly clear and we can move on, because I want to introduce you to how do you select covariates. That's one of the key things that I want to talk about today. Good? Well said. There's only one person who has spoken today, and that's usually worrying for me, because that usually means that people don't understand. Can I get thumbs up if you're following the class, or thumbs down if you're completely lost? Okay, I see a few thumbs up. Because you have taken the time to be here, it's important that you actually understand what's going on. Okay, one person says they don't understand. So if you don't understand, which part do you want me to go over the Poisson again?
Yes, sir. Please, you
Okay.
can go back again.
Okay, all right. So let me go over the Poisson again very quickly. I said that Poisson is for count variable. Okay, it's for count variables. Binary variables, 0 or 1, can be thought of as count variables, but it is up to the researcher or the analyst to interpret correctly. Okay, so this is very important, right? So that's why when you come across Poisson variables, Poisson models, you will see sometimes people will say it's a log Poisson model, but they're interpreting with risk ratio. Sometimes it's not, it's a log Poisson model, but they're interpreting with percentage. So it really depends on the variable that is the outcome. Okay, binary outcomes, I should say here. Okay, now Poisson is for count outcome variables. Always remember that we're interested in the outcome, not the exposure. That's the one that determines the type of model that we're using. Okay, so binary outcomes can be thought of as count variables, but it's important to the analyst to interpret correctly. The Poisson model in its basic form compares the mean. Okay, compares the mean. And so if you have like an example that we saw, and I call this example, this model fish, I can call this fish 1. And we said that it's a GLM model as well. And when you write the GLM and then you specify the outcome, if the outcome, and I should not use children because I think that's what's confusing. If the outcome is hours 80, hours greater than 80, which is a 0-1 variable for sure, and the exposure is whether a person is female or not, and the data is RDS, which is just our data set that we're using. We'll specify the family as Poisson and the length as the log. In this case, what we're trying to do is this is this binary variable 0-1, and we're asking R to obtain for us the risk ratio. So if we obtain the summary, if we use a summary statement to obtain the model output, and we obtain the beta estimate that looks like this and its p-value that looks like that, this we cannot interpret it like that. We have to exponentiate because we're interested in, because this is binary outcome. We have to exponentiate. So we have to exponentiate, and to exponentiate, we will obtain, and I can do this in one. We will exponentiate and we will ask for the coefficient function, fish 1. And we can ask for the confidence interval. So now we'll obtain the confidence interval 0.74, 0.38, 1.34. But the key thing to remember is that the outcome that we use here was a 0 or 1 outcome. And because it's 0 or 1 outcome, we are applying it as a count variable. It's not a true count variable. And the outcome that we're going to obtain is a risk ratio. And to obtain that outcome, we have to exponentiate. Okay? So that's the first form that we saw. And the second form that we saw is the one where we preserve the identity, which is the mean. And I said that the Poisson model is a model of the mean. Okay? And so here, let's use a more appropriate example, because I think the challenge there was the example that we used. So here, when we use a more appropriate example, and let's see if we actually have a more appropriate example here in our data sets. No, we don't. So we will have to use that example still, but you will understand that in real life, you would use an example that's appropriate. Okay. So let's call that fish 2. It's a GLM model. So we have this count variable, and that count variable, we're comparing it to, we want to see whether the number of children that females have differs from the number of children that males have. The family here is Poisson, and here we can have a link that is identity, or we can have a link that's log. If we have a link that is identity, what we're saying is that the mean, no, we didn't have the data. What we're saying is that the mean that female resident doctors have 0.20 more children on average than male resident doctors. The mean is 0.2. The mean difference. Okay. So what it's doing is essentially is that it is calculating the mean number of children among the male resident doctors and the mean number of children among the female resident doctors, and finding the difference between those two means. Okay. Debbie has a question. Yes.
Yes, just to clarify. So the last two regressions that you ran, both of them were log Poisson. And the only difference is that in the first one, your link was log, and the second one, your link was identity. And that's what explains the different outcomes. Am I correct? Or
both of them are Poisson.
Right.
Yes. And the difference is one is log and one is identity. I mean,
okay.
Yeah.
Okay.
And that leads to the difference. And I'm going to show that example again. So here, because we have the log, because I have the log, and okay, I'll summarize, and you'll fully get it when I summarize. So in this example,
can I just ask one other question? So you refer to the one where the link is log as log Poisson.
Yes.
If the link is identity, do you call it something else, or you just call it Poisson?
We just call it Poisson.
Okay, got it. Thank you.
So fundamentally, if even the log Poisson, if you just called it Poisson and said that your link was log, that would be fine too. Okay.
Okay.
Yeah. So people have different approaches. So let's look at this third variable, this third model, where here We are also looking at children. So let's call this fish 3. We're also looking at children. So GLM fish 3. GLM, sorry, children, tilde, and the exposure is gender, and we're getting the data equals RDS. Typing too fast, I'm making mistakes. And then we have the family. This is where all the drama is Poisson. And the link here is log. Okay. Fish 3 summary. So that's the summary statement. Okay. Here, when the link was identity, we said the mean difference. But when the link is log, the outcome, then we interpret this as percentages. Okay. So we can say that female resident doctors have 19%, 19.9% more children on average than male resident doctors. So to sort of summarize and tie it all together, what we're saying in essence is that for Poisson models, if the outcome, for binary outcome, okay, for binary outcome 0 or 1, you have to use the log link, and you have to exponentiate. Then you will interpret as risk ratio. Okay. For count outcome, you have two options. If you use the log, if you use the identity link, you interpret as mean difference. If you use the log link, you interpret as percentage difference. Is this clear to everybody?
Yes, thank you.
Okay. Yusuf, is this clear? Okay, all right. Let's switch over to talk about how do we select confounders. And for this one, I'm going to switch to my tablet. I didn't hear from Yusuf, so I don't know if it's clear to him or not, but maybe we can come back to, yeah, okay. So for this one, I want to write by hand. So all right. So we want to talk about selecting variables. Selecting covariates. Okay, to adjust for in your models. So this is an important discussion that we have glossed over. We have essentially been assuming that, you know, we've said, oh, you will include variables to adjust for in multiple regression. And this is what we have been doing throughout this course. Okay. there are two ways to make this decision. One is statistical, and two is based on subject matter. Okay? So the two is based on subject matter. And what we do in statistical is that, and so here people do different things. So it depends on who you ask. But this, I'll teach you one approach, which is the approach that I tend to use in my work. And and there's some citations for why this is a good approach. So in the statistical approach, you have multiple steps. Step one, or let me say broadly in the statistical approach, what you want to do is that you want to select variables that meaningfully alter the outcome. The outcome measure. So that means that if you're doing, so if you go back to the example that we were looking at earlier, where we obtained the log odds, okay, where we obtained the log odds, and this was when we're looking at the example of logistic regression, we're looking at the example of hours greater than 80 in relation to severe mental illness, right? And we obtained log odds of negative 1.2223 and odds ratio of 0.29, right? So this is a very strong effect, but this is unadjusted. So when you start adjusting, remember that when we did this last week, we adjusted for female, gender, age, number of children. And by the time we did that, the log odds after adjusting was only minus 0. Hold on, let me make sure that that's the same model. Okay, not the same model. Okay, not the same model, but the log odds after adjusting will change significantly. Okay, and I'm going to run this model quickly so we're dealing with the same exact log odds and we can see the effect. So when we adjust for gender, number of children in that model, we might obtain something that is like, let's say 1.05. Okay, 1.05, negative 1.05. So this variable is going from a very strong effect, right, to closer to 0. Now, in statistical adjustment, the question usually is, how do you choose which variables to adjust for? So in statistical adjustment, and this is the approach by these two gentlemen, or I don't even know who they really are. But these two people. And the first step will be to run multiple unadjusted models with each of the covariates of interest. Okay, so that means that if the variables that you're looking at, your outcome is severe mental illness, and this is the outcome. The exposure of interest is hours greater than 80. Okay. And the covariates of interest that you're exploring, you've collected data on these covariates. You have female, age, number of children, right, income, and you have multiple. So you have, let's say you have maybe 8 or 7. So you will now run a model. This is the model you're really interested in. Okay. This is the model you're really interested in. But you will now run a model comparing this to this, this to this, this to this, separate models. So here, if you have 4 covariates, you have 4 models. Okay. And for each of these models, you will look at the p-value. You will look at the p-value that you obtain in each of these models. If your p-value is less than 0. And this number depends on who you ask. If the p-value that you obtain ranges from less than 0.15 to 0.3, you will choose one before you start. You will say that, oh, I'm going to use, and I usually use 0.25. Okay, so it's kind of generous. If the p-value is less than 0.25, then that covariates moves to the next step. So let's say the p-value for female is 0.19, and the p-value for age is 0.35, and the p-value for children is 0.04, and the p-value for income is 0.03. Which ones will then move forward to my next step? Does anyone want to answer? Assuming that we're using 0.25, which is what I typically use. Anyone wants to guess?
Children and income.
Children, yeah, income. How about female?
Yes.
Yes, well,
Yes. Female.
Yes, exactly, female as well. So these 3, so essentially it's only age that will not move to the next step. Okay, now in step 2, we will take each of these ones that we're interested in, okay, each of these 3, and add them to this model that we're interested in one by one. So we will take this severe mental illness and hours greater than 18 plus. So in the first one, we'll add what? Female. We'll look at the log odds. Yeah. Okay. So first of all, we'll start by running this greater than 80. Look at the log odds. So let's say the log odds for this is, let's say it is 1.23, right? We saw that before, minus 1.23. So we'll run the next one. Hours greater than 80 and add female. And let's say we obtain the log odds here is minus 1.2. We'll run the next one. Hours greater than 80 and add children. Okay, and let's say the log odds here becomes minus 2.5. And then we'll run the next one. Hours greater than 80 plus income. And let's say the log odds here becomes minus 0.8. Okay. So now we have to make a decision and ask ourselves, which of these three should we keep in the model? And usually the way we will then make that decision is to look at these log odds, okay, and calculate 80%. So we'll look at which value, we'll look at which model changes this log odds by more than 20%. Okay, and really what we're trying to do is we're trying to ensure that if there is a covariate that really changes this model significantly, that we ensure to include them. Okay. So in step one, we looked at the values that the outcomes are related to the exposure, and anyone that is less than 0.25, right, we would consider it for this next step. Okay. And if there's any of these that increases this by more than 20%, we would include it in the model. Okay. So what that therefore means is that this one we would include, this one we would include, but this we might not. Okay. And then in the next step, we will implement a model that is a logistic, that is a multivariable regression. And here we will include the number of children. We will include the income. Okay, so this becomes our base now. Then we'll look at all the other variables that we kicked out along the way. So we kicked out female along the way. We kicked out age along the way. Okay. Now, we will now, one by one, add this into this model and look at what happens to the log odds. So if this log odds changes meaningfully, just like we did in this stage, if it changes meaningfully, so let's say the log odds for this in this multiple regression, okay? If this log odds in this multiple regression initially was, let's say, minus 1.5, okay? Now when you add female into it, it becomes minus 0.2 or whatever it is. I don't see how that's going to be possible, but let's say it becomes minus 1.1. And when you add the age into it, it becomes minus 1.48. So here you can see that with age, it didn't really change a lot, not significantly, but by a large amount. But with female, it changed by a large amount. So the model that you will then implement in your final model will become severe mental health, hours greater than 80, children, income, female. So this is one approach. This is one approach, statistical approach of doing this. Is this clear, or do I need to go over it again? Maybe, yeah.
Your explanation is clear, but is there a cutoff for what you would consider? So here you kind of just eyeballed it and said, well, 1.48 is not much different from 1.1. So you moved ahead with female. But is there some kind of cutoff that you would apply in the way that you had applied something earlier about greater than 20%?
Yeah, you could use 20% here as well. Yeah.
Okay, thanks.
Yeah, you could use 20% here as well. So this is one approach. But the key thing that I want to say is that, as you can see, the statistical approach is kind of complicated. It's data driven, so it depends on the result, the data that you have. And that means that if you implement today, somebody else using a data set in another study conducted somewhere else will get a different set of confounders or covariates, confounders or covariates to include. And so that means, because it's data driven, many people don't really like it. Okay. Still, the statisticians who like it and would insist that you include it. But the key thing that I want to say is that you should write out the approach that you want to use and say, this is what I want to do. Determine your thresholds. Are you going to use 20%? Are you going to use, like I used here, 0.25, 0.15? And some people would use 0.5 as p-values, right? At this stage, instead of using the log odds. And so multiple different ways that you could do this. But the key thing is that you should specify that this is the sequence that I want to use. Okay, so in statistical approach, you're using a combination of the p-values and the effect of the variable on the log odds when you on the log odds. Okay. Now, any questions? Can I get thumbs up if you understand it? If you think that, yeah, I think I should be able to implement this, it's just like mixed, or I'm completely lost. I see 2 thumbs up. That's not encouraging. Okay, if you don't understand it, can you ask questions so we can clarify? Because I'm going to go into the second approach quickly. Going. You should be comfortable to ask. There's a small class. If there's a small class, it absolutely means that you're the one who has taken the time to show up. And so you shouldn't leave the class without understanding what we're doing. Okay?
Sorry, one quick question. Just wasn't sure I heard you right. You're
Yes.
saying in step 2, you could also use a p-value. Some people do that. And it's a p-value of less than, did you say 0.5 or 0.05?
0.5, yes. Some people do
Okay.
this. Yeah.
Okay, thanks.
No, 0.05, not 5, not 0.5.
0.05. Okay.
Yeah.
I heard it wrong.
Yeah.
Thank you.
Yeah. So some people use 0.05 here. Okay.
Thank you.
So the key thing is that you should outline the sequence that you want to use. And All right. Any questions? None? We can move ahead. All right. So let's move ahead then. And the second approach is subject matter. Now, what you will do is that you want to, if you remember what we said a confounder is, we said that a confounder is one, a third variable that is related to the exposure related to the outcome and not on the causal path. Okay? The third variable that is related to the exposure, related to the outcome, and not on the causal path. Now, how do you know that the variable is related to the exposure? Is you have to understand, you have to have subject matter expertise. Okay? The example that we're using is simple enough. And so we can, so all of us can imagine the relationship of mental health and hours work, right? So we can already think about the fact that if a person is working too long, that it might affect the mental health adversely. Okay? So the exposure in this case is hours work, and the outcome is mental health. So let's take each of the covariates, and the first covariate that we will take, let's take the number of children. Okay. Can someone unmute themselves? Anyone who hasn't spoken today, preferably, or anyone at all, unmute themselves and tell us if people who have, if they think, and this is not, there's no, it's just what you imagine in your head. You think that people who have more children are more likely to work longer hours? Just how would you rationalize it based on your understanding? Anyone?
If I, yeah, go ahead, Yusuf.
Yes, I think people who have more children might tend to work less hours.
Okay.
Because they probably will get to work late,
Okay.
preparing their children. So they might also want to leave so early. So
Leave early, okay. Okay. All right. So you think it's related then?
yes, I think so.
Okay. So it's related to the exposure. Okay, very good. Related to exposure. Can someone tell us whether people who have more children are likely to have mental illnesses? Maybe they're more likely to be depressed or more likely to, be anxious. What do you think? Anyone? It's just what you think. It doesn't have to be absolutely correct. Yeah. But
I think they are more likely to be stressed.
to be stressed, yeah. Okay. So more likely to be stressed and therefore more likely to have mental illnesses. Okay. All right. So related to the outcome. Okay, good. Now, and here we have to pay a bit of attention. Do you think that if a person works longer hours, okay, leads them to have more children, which then leads them to have poor mental health. Do you think that a person who works longer hours is more likely to have more children and more likely to have poor mental health? Or the reverse, a person who works longer hours is less likely to have, maybe will have fewer children and then have poor mental health, or some way of thinking about it along this pathway, i.e., is the number of children, is it affected by the hours that the person works, which then we already know that the number of children, is it affected by, we already believe that having more children affects mental health. So do you think working long hours affects the number of children? That's the question. Anyone want to guess?
For me, I don't think it does have a direct influence
Relationship?
or direct effect the both. So I don't think
Okay.
it is
You don't think
the
so?
part of it.
Yeah. Okay. So does anybody have any concerns about this? So we therefore think that having more, the number of children a person has is not on the pathway. On the causal path. So finally, can anyone tell us if we think the number of children is a confounder of the hours greater than 80 and mental health relationship? Caroline, you haven't spoken today.
Yeah, so for me, since it doesn't lie on the causal pathway, it might not really be open. Of course, it could be, it might have relation to the exposure and the outcome, but not necessarily upon that.
But this is the requirement. Look at the requirement number 3. The requirement is that it should not be on the causal pathway. So because it is related to the exposure, it is related to the outcome, but it is not on the causal pathway. So do you think it's a confounder or not?
Okay, yes, that makes it a confounder.
Yes. So that makes it a confounder because it is not on the causal pathway. Because if it is on the causal pathway, it is something else, which we call a mediator. Okay? Because if it's on the causal pathway, it will be a mediator. If it is not on the causal pathway and it meets these other requirements, then it is a confounder. Is this perfectly clear to everybody?
Yeah, but sorry. So there is this example of people that drinks coffee and comes down with bladder cancer.
Yeah.
And effect of that is smokes. So what I understood for the example was that people that tend to drink more coffee also tends to smoke more, and so they tend to have. So that was an example that was usually being used as a co-founder. You are right.
So let's talk about that example. So people drink coffee, okay, and we want to see if they tend to have bladder cancer, right? This is okay. So this is the exposure, and this is the outcome, right? The question is, Is this related to the exposure? Is smoking is the confounder of interest? Is it related to the exposure? Are people who drink coffee more likely to smoke? What do you think?
Yes, they are more
Yes.
likely.
Is it related to the outcome?
Yes. Smoking causes
People
cancer.
who smoke are more likely to have bladder cancer. Okay, now here we have to pay extra attention. Is coffee intake, does it increase or decrease? Does it change smoking habits, which then affects bladder cancer? I.e., is it because of the coffee that their smoking increases or decreases? What do you think?
I think what I usually think is the coffee, for instance, now you might be a form of stimulant for them. So when they have
Yeah.
it, they tend to probably want something more. And so if they don't get it from the coffee, they might resort to smoking more. That's how I usually think about it.
Yeah, okay, so that's not really true. People who drink coffee coffee intake does not change smoking habits. Okay? Because if coffee intake changed smoking habits, then smoking would be a mediator, it would not be a confounder. But because coffee intake does not change smoking habits, right, then smoking is a confounder of the relationship of coffee intake and bladder cancer. Okay? And the many examples that you will come across, and sometimes one way that you will understand the example is what comes first. And I'll give you another one, for instance. So maybe that will help you clarify this funny issue. Okay. Now, in this same severe mental illness and was when we're looking at severe mental illness and hours greater than 80. So hours greater than 80 comes first. Severe mental illness. Let's take an example of gender. Okay, let's take the example of gender. Do you think that men or women work longer hours? You know, I mean, what do you think? Say you're working in a hospital, for instance, resident doctors, and you know the work is assigned by the leaders. And do you think that men or women work longer hours? There might be a rationale in some way there.
I don't think so. I don't think gender comes works.
You don't think so? Okay. Okay. All right. So among women who are, say, resident doctors who are in their 20s and 30s, and overall, some of them will get pregnant and then they'll be out of office for some months. And these days, men will get paternal leaves as well, but maybe the woman might get 3 months while the man will get 1 month. So we're not talking about every week when they're at work, but overall, on average, if you count the number of hours, the women might be more likely to go out on maternal leave or maternity leave, as it's called, right? And so that affects the number of hours that they might be working. So do you now agree that now that I've given you this way of thinking about it, that maybe men and women might work different hours on average?
Yes.
No, okay. All right. So that means that gender is related to the hours worked. Okay. Do you think that men and women have different levels of mental illness, anxiety, depression?
Yes, I think so.
You think so? Does anybody disagree?
Mm.
There is, in fact, research that has shown that men and women have different levels of mental illness, right? And so we can say that gender is related to severe mental illness. Okay, so that means that the first and second criteria have been met. The third criteria is whether it's on the causal pathway. And so you have to ask yourself, do you think that, based on everything that we've talked about, that hours greater than working longer hours, okay, affects a person's gender, which then affects their mental illness exposure, or maybe a person's gender leads them to work longer hours, which then affects their mental illness? Is there any of these pathways that
No,
you
I
think?
don't think so.
You don't think so? Okay, so which means that gender, obviously gender is, this one is clear, a person's gender is not determined by the hours that they work, right? So that one's clear. And this other one, you know, we know based on the way that we've thought about it, that men are not getting poorer mental health because they're working longer hours, right? I mean, so it's the other reasons why people are getting mental illness. It's not necessarily because of the relationship of the gender and the hours of the work. So these pathways don't really hold. So gender, therefore, could be thought of, if we agree with the way that I've thought about this, and you might disagree, okay? But if you agree with the way that I have laid this out, gender is a confounder. Okay? Gender is a confounder. Yeah.
Sorry, sir. So basically, what I just want to ask is, co-founder, when I think about it, is basically that something that can actually skew our conclusion when we make a certain conclusion about a certain
Yes.
analysis, that this is this. So
Yes.
confounder is something that can actually skew that. So when we say it shouldn't lie on the causal pathway, that means what I'm thinking is, in the right sense, it doesn't even have any effect between these two that we are trying to make a relationship between.
No,
So
no, no.
how
So that's
does
not
it
what it
then?
means. That's not
Okay.
what it means. What it means is that that effect that it is having, it's not in this pathway. I don't know. Maybe let me explain this differently by giving you an example that is not a confounder. Maybe that will help. Okay? Because we've only been seeing examples that are confounders. All right. And maybe I have to depend a lot on my medicine, and I hope that everybody can be able to get this. When a woman is pregnant, we give her iron supplements. Okay? We give her iron supplements. And those iron supplements, the reason why we do that is to impact the woman's risk of anemia. Okay? And we know that the woman's risk of anemia, okay, we know that the woman's risk of anemia is related to survival. Right? Women who are not anemic survive better in pregnancy. They're less likely to have, there's likely to be mortality there. Okay? Let me draw this differently. The line was too long. Anemia. Survival. Does everybody agree with this thing that I've drawn? Or does everybody understand it? As okay, this makes sense. We all know what anemia is, that's for starters. Is there anybody who doesn't know what anemia is? I haven't heard some people speak up, so I don't know to what extent they're following up with the discussion. So I'll carry on. If you have questions, please ask. Now, iron supplements affect anemia risk, affect survival. Anemia is not a confounder of the relationship of iron supplements and survival. So if a person told you that iron supplements are related to survival, if I said, oh, women who take iron supplements survive better in pregnancy, are less likely to die or something, or you will understand that correctly. And if I said that anemia is on the causal pathway between iron supplements and survival, you would agree with me. But here's the thing that you should also know is that some women will not have anemia, some will have anemia. If you give iron supplements to women who don't have anemia, it might not impact their survival at all because they already, maybe they don't have any anemia and they're just fine. But if you give iron supplements to women who have anemia, then it will affect their risk of survival. It will improve their likelihood of surviving. So the fact that this, anemia. So basically, the point I'm trying to make here is that anemia here is a mediator, not a confounder. Will it affect their? And so the question that we're asking is whether a confounder will affect the relationship. And the answer to your question in a long-winded way is to say that it's not only confounders that affect the relationship. It's not every time something affects the relationship of two variables that it's a confounder. There are other things that might affect that relationship. So if we come back to this example, if, for instance, the effect of iron supplementation on survival, let's say people who receive iron supplements in general are more likely than 20% risk of surviving. Or let's say the relative risk is 0.80. But if they were anemic, the relative risk might be 0.3. But if they were not anemic, relative risk might be 0.95. Okay? The fact that anemia affected the relative risks is not enough to make it a confounder. In fact, what we're looking at here is what we call effect modification. This is a finding that we actually want to see, we want to report it, because it will help us to understand the data better. But if we find a scenario where a relationship is obscured by a third variable, if we should pause and ask ourselves, does that make it a confounder or not? If it's on the causal pathway, it is definitely not a confounder. If it is not on the causal pathway, then it could be a confounder, and a variable could be both a confounder and an effect modifier. But the key thing I want you to remember now is that if it's not on the causal pathway, sorry, if it is on the causal pathway, it is definitely not a confounder. I don't know if I made this clear enough.
Yes, I think this example makes it more clear now. So I think I get that it's not only confounder that actually have effect on the relationship we're trying to measure. It now depends on how does it actually affect both the exposure and the outcome, and does it actually lies on the causal pathway. And the modifiers actually does almost the same thing, but this time it lies on the pathway. So I think I get it more better now. Thank you.
Excellent. Thank you very much. So there was one final point I want to make before we close for the day. And I was beginning to make that point. So if we go back to this graph, this relationship here that we're drawing by hand, right, and using it to illustrate the relationship between between variables, is what we call a DAG. Directed acyclic graph. Okay, directed acyclic graph. And so what we're basically doing is, remember, I'll draw this again. We said that we're looking at the relationship of hours, work, mental illness, gender. Okay, this is a DAG. What we're really doing here is that we said that the exposure, we can label that as A. The outcome, we can label that as Y. And we have a third variable which we label as Z. And we said that this third variable is related to the exposure and it is related to the outcome. Okay? When we use line graphs like this to represent the relationship between variables, okay, this is what we call a DAG. So, key point to take away. When you look at a DAG, you can tell whether a variable is a confounder or not. Okay, when you look at a DAG, you can tell whether a variable is a confounder. Or I should say that based on the DAG, we have another definition of what a confounder is, which is a common cause. Okay, look at Z is related to A and Z is related to Y. Both the exposure and the outcome they're sharing something which is a common cause, and this is the confounder. Okay, so that's another way to think about confounders, but this is a DAG. And you could actually present this DAG in your paper, right? So you draw a DAG that represents all the confounders that you thought about. So instead of going through this list statistically like we went through, you'll go through this list based on subject matter, and whichever variables then qualify as confounders, you will add them to the model. So based on that, you will add maybe female, children, age. So even though age did not meet your statistical qualification, you will still include it if it is a confounder based on subject matter. And there is now a third approach, which is a hybrid approach. The hybrid approach. More often than not, this is what I do in my papers. In the hybrid approach, you will include variables based on subject matter. And then the variables that you cannot include based on subject matter, you will evaluate them statistically. In a disciplined, as a disciplined epidemiologist, you will refer to these ones as the confounders. But these will be covariates that you still include. So you will say all of them are covariates. They're all covariates to include. That is a hybrid approach. Okay. So over the last hour or so, I've painstakingly explained the statistical approach for selecting covariates, or at least one statistical approach for selecting covariates, and some variations of that approach. I've also gone through the subject matter approach for selecting covariates. So I want to ask, and I've also mentioned that you can use both. Now that you understand it, which do you all prefer? Anyone? I mean, let's just go through the class and you tell us, well, I think I prefer the statistical, I think I prefer the. So, what do you think, Debbie?
I think the hybrid approach. The only issue now is how do we actually
No, Yusuf, you can go ahead. I think you have started. You're taking the floor. So.
because I was saying the variables are actually left now. How do we know that? Do we just run all variables that you have, or you first look at which one can actually have some level of co-founding to your relationship? Because what I'm thinking now is I might probably have forgotten to collect some certain data as regard to what could serve as a co-founder. Then when I start my analysis, I start seeing like I should have had this data. So do I still feel like I should just leave it out? Or because if I want to use this model, that means that has to come in as possible something.
Yeah,
I'm just thinking, and why I'm saying this is okay. Thank you.
Go ahead, finish your thought.
I think you got I wanted to give an example.
Yeah.
I think you got my question.
Yeah. So it's a very good question. And this is why when you're planning to do research, from the very beginning, you have to have thought about the statistical analysis from the beginning. So at the time when you're collecting data, you're already thinking about the statistical analysis. So if you think that something might be a confounder, you should already collect that data from the beginning. Okay, so if you don't have the variables, there's nothing you can do, right? But if you have the variables, you should evaluate each of them as a possible confounder. Okay, so yeah, so good point that you placed. Thank you.
Okay, right.
Yeah. Okay, anyone else? What do you think? Which do you think is your preferred approach, the statistical or the subject matter approach?
I think even without thinking about it, now that you've presented it this way, I would think the hybrid is the best or the best approach of the three. But I think intuitively, before this, that's what I would do. I would think about what, based on my knowledge of the field, what are the things that are possibly going to be affecting the relationships, whether as confounders or as mediators. And then I would put those into, I'd do univariate analyses with those, or bivariate analyses with those variables. Yeah. Anyway, so I think intuitively, that's what we tend to do.
Yeah.
Without even realizing that, we're doing the hybrid model.
Yeah. Okay. Good point. Thank you. Anyone else have any alternative thoughts? Push back and say, because I have a pushback, and that is to say that with the statistical approach, you can clearly define the list of confounders based on, so you outline and say, this is my threshold, this is what I used, and anybody who takes your data will have the same list of covariates to include. But with the subject matter approach, it's a little bit of fuzziness, right? Like if you remember, as we were going through the example, I was saying that gender, for instance, is related to severe mental illness. And some people might not agree, right? So if a person does not agree that gender is related to severe mental illness, they might not think about it as a confounder. And so their list of confounders will then be different. Okay. So there is a little bit of subjectiveness that gets introduced in the subject matter approach. Okay. But one way that we get around that subjectiveness is that we ask people, don't just reason it from your head. Look for publications. Okay. So you see where we're going through the point and saying related to the exposure, related to the outcome, or we're answering these questions. For each of these questions, you would look for papers, that have looked at the relationship of the exposure to the covariate they're evaluating, the outcomes of the covariate they're evaluating, and at least those two you will provide as evidence those papers, and so you will cite those papers in your methods. So you say that you selected this covariate as confounders, blah blah blah, and then you include the citation. So that's one way where we try to reduce the subjectiveness of the subject matter approach. Okay? So that's important to remember that there's the potential subjectiveness. The subject matter approach is intuitive, it makes sense if you know what a confounder is, but then there is that potential for subjectiveness. And so the way we get around that subjectiveness is to ask that you cite the papers, so you don't just bring it from your head alone. Okay, you cite the papers that back up your claim that this could be a compound. All right. Thank you very much for sticking through. This has been a very long discussion. Any final questions?
I just have one. So
Yes.
the lab 5 that you made some additional annotations on.
Yes.
Could you share that with us, please?
Okay, I will do that.
Thank you.
Okay, excellent. Thank you very much, everyone. We will talk to you again soon. Enjoy the rest of the day.